Hi, this is the first assembly language lecture on data types. There's some recommended reading about signed numbers on the wiki, two's complement numbers on the wiki, and fixed point and floating point. I want to thank Mark Clement of Brigham Young University for most of this material. So here's what we're trying to do. Hopefully you'll be able to do this when you're done with listening to these videos. Students will be able to represent an integral number as an unsigned or assigned ones or twos complement integer, a signed magnitude number, and an ASCII character. You should be able to represent fractional decimal number in fixed point and floating point formats, convert a binary number to decimal format, convert a decimal number to binary format, articulate the use of computer word size, endianness, sign extension, and number overflow in developing computer programs. So we need to know about binary digital systems, hexadecimal numbers, integral data types, that means unsigned, signed magnitude, ones and twos complement, overflow. We need to know about word size, sign extension, and converting decimal to binary. We need to know about fractional data types. Those are fixed point and floating point. We also need to understand ASCII characters and how they're represented, and we need to understand casting and a thing called endianness. So let's start out with a simple question. What are decimal numbers? Decimal means we use base 10. We use 10 digits, 0 through 9, in the representation of our numbers. So there's the symbols. They go 0 through 9. We have 10 of them, 10 symbols. We use what's known as positional notation. The position of the digit denotes how many tens it represents, or 10 to what power it represents. This is most widely used by pretty much everybody these days. So what does the number 3,546 mean? It really means 3 times 1,000. You got plus 5 hundreds, plus 4 tens, and 6 ones. That's 3 times 10 to the 3, plus 5 times 10 to the 2, plus 4 times 10 to the 1, plus 6 times 10 to the 0. Notice that this is the, start out at this position. This is 10 to the 0 position, 10 to the 1 position, 10 to the 2 position, and 10 to the 3 position. That's what these numbers right here, 10 to the whatever. So how about negative numbers? We need more symbols. We put a minus sign in front of this whole thing to make it negative. So what are binary numbers? Binary means we have 2 digits, just 2, to use in our representation of numbers. The symbols that are commonly used are 0 and 1. We use positional notation in the same way as we did with base 10. It's more adaptable for computers because you can have just 2 levels. Now, computers could be designed to use 4 levels or whatever you want, but it's just easiest to use 2 levels. So what is the decimal value of the binary number 1011? Well, let's see. That this one right here is 1 times 2 to the 0, plus 1 times 2 to the 1, plus 0 times 2 to the 2, plus 1 times 2 to the 3. And 2 to the 3 is 8, and 2 to the 2 is 4, and 2 to the 1 is 2, and 2 to the 0 is 1, so that's what it means. So you can see how that all works out there. How about negative numbers? We don't want to add an additional symbol. We've only got 2, right? Yikes, what are we going to do? So let's think about things. Anyway, let's think about the binary digital system. What is a binary digital system? Binary, base 2, means there's 2 states. Digital means there are a finite number of symbols. A basic unit of information is the binary digit, or bit. How are bits represented? Well, by voltages usually, sometimes by residual magnetism and things like a hard drive, sometimes by light, sometimes by polarization, and sometimes by some other things. What about more than 2 states? A collection of 2 bits has the possibility of 4 states. If you have 3 bits, you can have 8 states, and a collection of 2 to the n bits has 2 to the n possible states. So let's look at the electronic representation of a bit and get a better idea how it works, especially in the terms of voltage. Now, analog processing requires exact physical values. So the way we used to do things, like for example, to build a radio, we'd have a wire, an antenna hooked to the input of some electronic circuitry, and all that electronic circuitry would process the electronic voltage received at the antenna. In other words, the circuitry, the mathematics that describe the circuit equations, would be what you wanted to do mathematically to that voltage that's coming in the antenna to make it sound like Sandy Patty singing or whatever the radio station was playing. Nowadays, what we do is we have the same antenna hooked to an analog to digital converter, and then we have a stream of binary digits coming in, and we take those numbers and we do all the mathematics to those in a computer or often a field programmable gate array, some kind of digital logic circuit, and eventually we run it back through a digital to analog converter and play it out the speaker. So there's advantages to using non-analog values. See, analog values are never quite the same. And if you think about all the components that were in those circuits, those were probably plus or minus 10%. And, if you were doing mathematics on things and you could only do plus or minus 10% on all your numbers, you wouldn't be able to do a whole lot. And that's the way it is with analog. Each time you play a vinyl album on your record player, it will sound a little bit different because each time you play it, it wears down the vinyl, and pretty soon it doesn't sound exactly like it did before. Usually there's little scratches and things, make pops and things that weren't supposed to be there. So bits rely on approximate physical values. And so they can be off by quite a bit, but the analog value can be off by quite a bit because it's anywhere in this range will do to represent either a 1 or a 0. And these things are not generally affected by age or temperature in the same way as analog signals are. So you get music that never degrades. You guys know about that. That's probably about all you know about. You probably never listened to the old-fashioned kind of things like a vinyl recording. Pictures that never get dusty or scratched. And all kinds of nice things like that. Computers rely on approximate physical values. In other words, a logical 1 might be anywhere from 2.4 volts to 5 volts, perhaps. A logical 0 then would be related, or be in the range between 0 and 0.5 volts, and then that leaves you with a range in the middle, which is illegal, and if you get that, an error will pop up. So, this is really, in some ways, revolutionary. So, we need to learn some new names about binary things, so let's try and do that. We group bits together to achieve higher precision. For example, 8 bits can give us better precision than 1 bit by a factor of 1 over 256. There's 256 levels. 16 bits can give us 65,536 levels. So you can make a lot more precise with 16 bits, and 32 bits is even more than that, and 64 bits is an incredible amount. And so there's these things, the numbers that kind of go with all these different levels, And we should learn some of the names here. You guys are probably familiar with a lot of these. A byte, what a byte is, that's 8 bits. And then a kilobyte, well, that's 10 to the 3 bits, or 1,000 bits. And then there's this thing about a kibibyte, and that's 2 to the 10th bytes, so 1024 bytes. And then there's a megabyte, which is 10 to the 6th bytes, or a mebibyte, which is 2 to the 20th bytes, and approximately equal to a megabyte. Gigabyte, 10 to the 9th bytes, and that's about equal to a gibibyte, which is 2 to the 30th bits. Or 2 to the 30th bytes, which is 8 bits, so, you know. So anyway, there's a bunch more here that are like incredibly big, and I'll just pass through those. You can look at those at your leisure. Let's look at a way of trying to understand or read binary data. It's really a problem when you have a long string of ones, which you actually need a long string of ones. You know, if you're going to write a very big number, you just saw you need a lot of digits in base 2, many more than you need in base 10. So it makes it kind of verbose and hard to read. And so what we came up with is a thing called hexadecimal. So we group all the binary digits in groups of 4, and each group of 4 binary digits could be written in hexadecimal with 1 digit. Now hexadecimal digits, that's base 16, there are 16 symbols. So we use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And A is basically equivalent to 10, and B is 11, and C is 12, and D is 13, and E is 14, and F is 15. So you can kind of see how that works. There's a nice little conversion between the 4 bits and the hexadecimal digit on the right. And so if you look at something like you're seeing there, you can just put these hexadecimal digits together, and it's very much easier to read 478F hex than it is to read 010001111110001111. And you know, I mean, it's hard to even keep track of how many digits I rattled off there when it's binary. So as you see, you separate the bits into groups of 4, and then translate each digit into a hex digit. You can see that here. There's the 4, and there's the 4. 0x is a common prefix for writing decimals, which means it's writing numbers, which means it's in hexadecimal. Okay, so what kind of data do computers use? Basically, yeah, you know, in computers you want to be able to use numbers. That's all kinds of numbers: signed, unsigned, integers, floating point, complex, rational, irrational. You'd like to be able to use all those things. And you'd like to also be able to use text, you know, characters, strings, and so on. Images, you know, pixels, colors, shapes. Sound, pitch, amplitude, logical, you know, true, false, yes, no, on, off. Instructions like programs, man, you have it. There's a pretty much you'd like to be able to the computer to do practically use any kind of data. So what is a data type? It's how the data is represented. What operations are valid for those data? So let's look at some examples. And these are important data types. So you could have unsigned integers. Those are non-negative integers, you know, 0, 1, 2, 3, 4. We need to be able to represent those in the computer. We need to be able to represent signed integers, you know, like -1, -2, -3, or 0, 1, 2, 3, 4, you know. You want to be able to represent fixed point numbers. Those are bounded negative, 0, or positive numbers with a fraction. And floating point numbers, those are more unbounded negative. I mean, they actually are still bounded, but they're much larger. You can go much larger with floating point numbers than you can with fixed point. And we'd also like to be able to represent characters like 1, 2, 3, and ABC, and those kind of things. So let's look at integer types of data. First of all, there's unsigned integers, and computers use weighted positional notation, as we discussed before. Like, in base 10 we got 329, but in binary, you got 101, and the first one is 1 times 2 to the 2, and 0 times 2 to the 1, and 2 to the 0, 1 times 2 to the 0. You add those up, you get the number 101, which would be 9, I guess. No, 6. No, 5. Anyway, how do these unsigned binary numbers, or what do these unsigned binary numbers represent? Well, they can represent, unsigned binary numbers or unsigned numbers. So here's some examples. See if you can figure this out. This is kind of a quiz here. So we'll let you think about it, and then we'll give you the answers here in a minute. There's the first one. There's the second one. The third one. Okay, so you had a little practice there. Now how about arithmetic, unsigned binary arithmetic? Can we add things just like we do in base 10? Well, turns out you can. So you start out on the right and you add, in this example, 0 and 1, you get 1. 1 and 0, you get 1. 0 and 0, you get 0. 0 and 1, you get 1. And 1 and nothing, you get 1. So there's an answer. So let's do one a little bit more exciting here. So 0 and 1, you get 1. 1 and 1, you get 2, but that's a 0 and a carry the 1. And 1 and 0 and 0, you get 1. And then you can keep adding them up. Here's one that's even maybe a little more interesting. 1 and 1 is 2. You got to carry the 1. And you got 2 again, and you carry the 1, and you carry the 1, and you carry the 1, and whoa, now we got one more digit. And one more here. At the bottom, 1 and 1 is, you got to carry, 1 and 1, carry, 1 and 1, carry, 1 and 0, no carry, and then 1. So there's a little practice for you. Try subtraction, multiplication, division. Can you figure out how to do those? Okay, so let's do a quiz here. You can look at this quiz and come up with some answers. And then we'll go on to the next lecture.